Welcome back to CS 520. Today I'm going to talk about linking. Linking is obscured by the tools that we use under Linux systems, in particular GCC. When you run GCC, it just magically produces an A.out, but there's actually lots of steps to get to an A.out. This diagram tries to show them to you. In particular, if you are compiling two C files, what the compiler is going to do is actually compile each C file individually into an object file, and then the linker is asked to combine the two object files together along with C libraries that contain things like printf in order to produce your A.out. So there's several steps in here, and in fact this diagram actually doesn't show you all the steps. But we're going to be focused on this block today of how do you take object files and combine them together to produce another object file, because that's really what an A.out is. An A.out is an object file where all references to symbols are defined. And just to show you how much stuff is going on under the hood when you run GCC, here's a display of me running GCC with a verbose flag -v on two C files. In this case it's a program here to emulate the VM520 machine and a test file, and I'm linking with the pthread libraries because I am using threads to implement the various processors of the VM. And here's what comes spewing out if you do that. I've tried to highlight in red actually the relevant things. It's showing us lots of flags that are being set by default, but down in here we see first of all CC1 running. That's actually the C compiler running on both.c, the first of the two C files. And it's actually producing not an object file as my diagram would have led you believe, but rather an assembly language file. So the C compiler is actually translating the C into human readable assembler. And then further on down the page you see the assembler running, AS, the Unix assembler running, producing an object file from the assembly language file. So in fact there's two steps there. The C compiler generates assembler, then the assembler generates object code. Then you see the same thing, same series of steps happen for the second C file. C compiler running, generating assembly language file, the assembler assembling that assembly language file into an object file. We flip the sheet over here to continue this trace, and later on we see something called collect2 being called, and it's analyzing the object files and also considering libraries. The pthread's the one I included, as well as a bunch of standard C ones included down below. Collect2 actually is there because it handles the automatic generation of C++ constructors when necessary. It's running just to see if we have any C++ constructors that need to be created. But collect2 itself invokes LD, which is the actual linker, to combine these O files together and to search these libraries and pull in any additional object files that are necessary for things like printf. So you might, for fun, try to do that sometime with your programs. Just run the -v flag to GCC and you'll see there's a lot more going on than you may think. And again, today we're focused on sort of that last step where the linker runs and combines object files together. Before we dive into the details though, we need to think about addresses. It turns out there's different types of addresses on different types of machines and in different types of contexts. So you'll hear people talk about absolute addresses, and these addresses don't change no matter where the program is placed in memory. The address is absolute. It's not relative to the location of the code. Rather, it's absolute. It's specific to a particular location in the machine's memory. You'll also hear people talk about relative addresses, which means the address is relative to the piece of code it's included in. This usually assumes the program is going to be placed in memory at address 0. So the piece of code assumes that the first piece of code, it will be at address 0, and everything else is relative to that. Okay, we'll see those kind of addresses in the examples we do today. And then, since you've looked at the VM520 machine, and you know there's PC relative addresses. So the bits that are inside of instruction that contain an address are meant to be added to the program counter in order to get the absolute address. And we'll see the advantages of this. The main advantages of this are the following: is that the linker or the loader may need to adjust relative addresses, but would never need to adjust an absolute address because it's absolute, or PC relative addresses, which are not absolute, but they automatically adjust no matter where the code is placed in memory. And what do I mean by the loader? The loader is what puts the program in memory for execution. So it takes an A dot out and puts it in memory. So if your machine has relative addresses, as the loader brings a program in and places it, let's say, starting at address 1000, the compilers and the assemblers have assumed that the program, for the time being, was going to be placed at address 0. The loader will actually make that adjustment, right? It'll add 1000 to all those relative addresses, right? So if I'm loading a program that was assembled assuming it would begin at address 0, but I actually loaded in at address 1000, the adjustment that the loader would need to make would be to add 1000 to all the relative addresses. But if I load a PC relative, a program containing PC relative addresses, doesn't matter where I place it in memory, right? All the addresses are expressed relative to what the program counter will be at runtime. And that's, if you think about that, that's sort of automatically adjusting the addresses, and there's no additional effort needed by the loader. And the same thing will hold for the linker, as we'll see. So the key task for the linker is to handle situations where one file uses a symbol located in another file. In other words, the user in a C program is calling printf, right? I'm using printf, but it's going to be defined in an object file that's located in a library. So instructions that can reference the symbol contain holes that must be filled in. Right, when the assembler assembles my call to printf, it doesn't know where printf is going to be, so it has to leave a hole in that instruction. And when the linker includes the code for printf into the program, the hole will have to be filled in with the actual address of printf. That's the main task for a linker, to do that kind of operation. Let's just review some terminology. We've talked about this already in the context of VM520, but end symbols, what do we mean by that? Those are symbols that are defined in the file and exported out of the file. So the writer of printf would define printf and then indicate that printf should be exported and be allowed to be used by other files. Out symbols are the reverse of that. They're referenced and they're imported. So when I use printf but don't define it, I'm referencing it and then I'm expecting it to be imported from another file. So I call those out symbols. And we know the VM520 object files have that kind of information in them, as do object files on real systems, by the way. But the picture then is something like this. The linker is a program. It's reading, let's assume, 2 object files for now. Those object files have object code, the actual encoded instructions, but they also have symbol information. They have a list of symbols that have been defined and are exported, and they have a list of symbols that were referenced and are hoping to be imported. And what the linker wants to do is combine those two files together into one output file, where the main thing is that the object code is concatenated together, right? This file has the code for both portions of the program. Again, this might be a user program that's using printf, and this might be the code for printf. So in the final program, we want both the user code and the implementation of the functions the user code is using that are being pulled out of a library or somewhere. And moreover, we want to have in symbol information and out symbol information for the new result, because this might be the first step. We might have to link this program several times to bring in code from a variety of libraries. So the linker actually is usually set up that its input files are the same structure as its output files. We produce another file that could be sent to another round of linking. Let's look at the linking algorithm. Step one is what I said is the main job, right? We're going to physically put the object code together from the two files. Concatenate that together so it can be put out into the output file. These other steps are a little bit more subtle, however. What do we have to do? We have to adjust the address fields in in to and out to by adding the length of object 1. So again, I'm not talking about addresses inside the program at the moment. I'm talking about addresses in the in symbol section and out symbol section. Again, the addresses in the in symbol section and the out symbol section are usually relative addresses. They talk about things relative to the beginning of the file, of the object code inside the file. So those are relative addresses, assuming that the first thing is at address 0 in essence. So the second file, though, the code for the second file is going to go after the code for the first file. At least that's how I drew it in the diagram. Somebody has to go first. Let's assume object 1 is going to go first. So the code inside object 2 is no longer starting at 0. Rather, it's starting, right, this distance here is the length of object code 1. So anything that's talking about object code 2 and thinks that this boundary starts at 0 needs to be adjusted and have the length added to it. That's what I'm talking about in step 2 here. Right? When I'm talking about addresses in the second object code, I now have to add to them the length of object code section 1. So I have to make that adjustment. Step 3 is I can combine the in symbol tables now. These are the things that are being defined in each individual file and exported. And what I want to place into the output file is just the union of those two. All that stuff now becomes visible outside. And the only tricky thing is I have to look for error conditions, right? Error condition would be if there's something in the intersection, right? If they both define the same symbol, that's probably an error that we need to report. If the intersection of the in symbols from file 1 and the in symbols from file 2, if the intersection is not the empty set, then that's a duplicate symbol error that we need to report. Okay, finally, step 4 then is to match up out symbols in one file with in symbols in the other file. So I'm going to, I said in here, but I'm assuming only 2 files in this diagram, so let me change that to a 2. So I'm looping over both files, and I'm looking in the out symbol section for each file. So if there is something in the out symbol section, let's call it X. And what I want to do is now look it up in the new combined in symbol section that includes the in symbols from both. And if I find it, then I want to go ahead and then insert the appropriate address into the instruction referencing X. Right? Because if I find it in the in symbol, it's defined now, so I know its address. The address has been adjusted in the second files to be relative to the combination of the two object codes sections. So now I can compute the right address and put it into the instruction that's referencing X, essentially filling in the hole that's in that instruction. However, if I look it up in the in symbol table, look X up in the in symbol table and I don't find it, if X is not in that combined new in symbol, then it remains an out symbol and needs to be put into the out symbol section of the output file. Okay, this linking algorithm here assumes that addresses and instructions are PC relative addresses. I guess it also would work if they were just relative addresses as well. So maybe I should write that, or relative. Okay. Well, to make this algorithm concrete, let's look at a VM520 program that consists of two files that we need to link together. So here's some VM520 assembly language. This is in essence a main program that's going to call an imported function called get42. It's going to call it twice. So it calls it twice and essentially adds the two return values together and stores that in a result variable, which can then be examined by the outside world. Yeah, that's the way VM520 programs work, is they're run in the context of a C program actually. So your virtual machine runs in the context of a C program. You run the virtual machine and then you can explore the virtual machine's memory to get any answers out. A few other VM520 details here. One flaw, I think, in my design for VM520 is the frame pointer is initialized to 0 when you start up the virtual machine. But you really need that frame pointer to be set. So most programs that are going to call functions and use the runtime stack are going to have to set the frame pointer. Here I'm just setting the frame pointer by adding the stack pointer to the 0 that's in the frame pointer now. So now the frame pointer and the stack pointer are together. Maybe we should just walk our way through this program because it might help you understand how functions execute on VM520. So I load immediate 4 so that I can subtract that from the stack pointer. What this is doing is stacks on this machine grow from high memory back to low memory. The stack pointer has been set to be up in the high memory. So what we're doing is we are allocating a local slot here by adjusting the frame pointer. I'm subtracting from the frame pointer because the frame pointer used to point here. I subtract 4 from it and bring it down here. I'm allocating a local slot. So this is a local slot. Then I call get42. And the call is going to push things on the stack. It's going to push the return address. It's going to push the frame pointer. It's going to establish a new frame pointer. Okay. So the stack continues to grow down from high to low memory. Then I do the call instruction. I go off to the function. When the function returns, the stack will shrink back. Okay, so that's how the runtime stack. Again, I don't have a recursive function here, so it's pretty straightforward, but the stack is just going to grow for the first call to get 42 as I remember the return address on top of the stack and the old frame pointer, and then it shrinks back. Notice the local slot that I allocated here is going to be accessed as a negative offset off the frame pointer, because where is the frame pointer pointing? The frame pointer still points here to where it was initialized up in this instruction. The stack pointer has been subtracted. It points down here. Okay, and the -1 will point to the to that local slot, which by convention is where a return value is placed. Okay, so the frame pointer is important in order to access parameters and also local variables. So when you do a call, it's going to be saved along with the return address and then reestablished upon the return. Again, you should take a look to understand this better. You should read the VM520 documents and understand how call and return works. Sorry I got off on a tangent, and let's get back to linking. The point is I've got one file that calls a function that's not defined in this file. Get42 is not defined in this file. Rather, get42 is defined over here in a separate file. In this file now, get42 is defined. It's a very simple program. It just loads 42 into a return, into a place on the frame, and then does a return. Okay, and the get42 symbol is exported. Okay, so the goal, the linker then is going to be to combine these two files together. Right, we want to put this code together, but it's going to be done not at the assembly language level, rather it's going to be done at the object code level. Because the first step we would do is we would assemble these two programs into two separate object files. Let's take a look at those object files. Which one is this? This is the main program, I guess. So this is a disassembly of the object code that was produced by assembling the source code we just looked at. You'll see in here the main program has an in symbol called result, so that the outside world can look in and grab that result value. It's at address 10 is the way you read this. These addresses are being given in decimal, by the way. And it has two out symbol records, both for get42, because there was two calls to get42. One is at address 5. I highlighted that in green here. It's the call instruction. Notice the disassembler says, oh, that address must be undefined. You know, that's essentially a hole. And the other one is at address 3, which again is a call to an undefined location. And there's zeros bits in those holes right now, just because there has to be something in there. But those are holes that the linker will need to fill in. And what have we got on for the other file? We assemble the other file. We look at that object file. It has an in symbol called get42. It's at address 0. Again, it's a relative address relative to the object code inside this file. So that says that get42 is at the beginning of the file. There are no out symbols. We don't use anything else. There's no holes in the code. So what the linker is going to do is going to concatenate this code together. First step, right? Is concatenate this code together. You can see that the code in the first file is 11 words long. So that means these addresses down here all have to be adjusted, right? They have to have 11 added to them. So this one becomes 11. This one becomes 12. This one becomes 13 in the new combined object code. Okay, so that's sort of step 1. I'm going to go back to my outline for the algorithm. Right, step 1 was physically put the object code together. Step 2 is adjust the address fields in the in symbol and out symbol section for the second file. Notice the first file, the 5 and the 3 in the out symbol second are still good, right? Those are because they didn't have to adjust. They're going first. The beginning of the code is still at address 0. And the result is at slot address 10. That's still good. But in the second file, get symbol is no longer at 0. Rather, it's at 11. Okay, so that's step 2, is adjust those. Okay, step 3 was actually combine the in symbols sections together. So the combined in symbols for the result, right? The in symbol for the result is going to be the label result is still at address 10, and get42 is now at address 11. That's the end symbols of the results when we add those together. Okay, that's step 3 to bring those end symbols together. Step 4 then is to try to resolve any out symbols look up any out symbols in either file and see if they're in the new combined in symbol table. Okay, in this simple example, I only have one out symbol. It's in the first file. I have one out symbol, but it has two occurrences. So I look up get 42 and the result is now address 11. Okay, address 11. So I need to fill in, let's do the 5 first, since it's in the list first. So I'm at address 5. Remember, how does this work? At runtime, we're going to take the PC plus the stored address, and that's going to be the actual address. So at runtime, when this instruction is called, the PC will actually not be 5, it will be 6, right? So what do we want to store? We want it to produce get 42, which is at address 11. So what we need to have stored is actually 5, right? So stored equals 5. So what would be placed into this address field, this one here, would be 00005. We'd fill that hole in with a 5. Okay. So that takes care of this one. We do the same thing. We get 42.3. Now the PC at runtime is going to be 4, and we're going to need to add to that, obviously, the stored is equal to 7, right? So this hole would be filled in with 00007. Okay, and that would take care of the second out symbol record. And that's it for the first file. Then we go look at the out symbols for the second file, but there are none, so there's nothing to do there. So in the result then, what are the out symbols? It's empty, right? The out symbol section would be empty. There are none. And now the linker's done, and it can output the new object file. Now it knows what the in symbols are, it knows what the out symbols are, it knows what the updated code looks like, including having the holes filled in. And the resulting program is ready to be executed. Okay, so that's a quick example about how a linker would work. We're not going to do it in the course, but you could sit down and think about writing a linker for the VM520 system. Alright, so a few other details here. What about libraries? What exactly is a library? Well, it's a collection of object files with indexing. You want to be able to quickly look up a symbol name like printf and figure out which object file contains printf. And then pull that object file out of the library and send it to the linker to be linked with the user's code. One thing to note is that printf itself may use other things that are in the library. So there's sort of a recursive nature here that we bring in printf, and printf may introduce additional out symbols, which means other things get pulled out of the library. And in fact, there can be, as I alluded earlier, there can be cross-library references. So you may have to continue this linking operation for a while to resolve everything. Right, an object file from one library might itself have out symbols. So then you go out and resolve those out symbols. But a library is just a collection of object files, so it doesn't, the concept of a library doesn't fundamentally change the idea of what a linker actually does. It just means your linker has to be able to go out and search for symbols, pull object code out of libraries, and then link them in as we just described a moment ago. One other feature of modern systems is that they often use dynamic linking. I've been talking about static linking, doing linking ahead of runtime. But on modern systems, we often do linking at runtime. Right? What do you mean by this? Well, code is loaded into memory upon demand while the program is running. So again, we're seeing von Neumann's design come to fruition here, right? We can modify the program while it's running. The program itself can be smart enough to add code to itself. Why would you want to do this? Well, we'll talk about virtual memory later in the course, but virtual memory allows us to share code across multiple running programs inside a system. So, you and I are running our programs. We're both using printf. Do we both want a copy of printf that's sitting in physical memory? Or can we share a copy of printf and have one piece of code in memory and we both are using it in our program? So that's one thing, is that rather than loading it statically, we might wait and look around at runtime and see if it's already in memory and then just link up to it. Another thing people notice is a lot of code never gets executed. So error case code, for instance, is there in case something happens, and bad things often don't happen. So we might have leaner programs that take up less memory, by running them and only bringing code in when they're actually needed. That's a couple reasons why dynamic linking is done. Another factor is you just have smaller object files. You just, again, you only bring the code out of the library when you actually run the program, rather than storing it on disk in your object files and having printf replicated a billion times on your system and everyone's programs. Okay, so just a quick spin through how dynamic linking works. One way to do it is through something called a procedure linkage table, a PLT. So calls to dynamically linked functions is done via the PLT. Each PLT entry contains the address of the dynamic linker initially. The first time a function is called, the dynamic linker is actually called. So, you're calling functions indirect through a table of addresses. And the function looks like an index into the table initially. But what's in the table at initially is the dynamic linker code itself. So the first time you call a function, you don't get the function, you get the dynamic linker. The dynamic linker wakes up and it knows its job is to go out and find the actual code and bring it into memory. So that's what it does. It loads the code, resets the PLT entry to be the address of the new code. So the next time you call the function, you'll go right to the function. Then you re-execute the initial function call so that on the first call you go to the recently loaded function. So again, a little bit of trickery. An indirection array allows you to call a function indirect, and the first time you call a function, you don't get the function, you get code for the dynamic linker. The dynamic linker knows how to go find the function you're trying to call. Dynamic linker knows how to go locate the function in a library that you're trying to call, bring the code for that function into memory, do the linking operation like a static linker would do, and then put the new address into the PLT entry and then re-execute the function call. Then on subsequent calls to the function, you'll go directly to the code that's been linked into memory. So that's a very quick view of how dynamic linking can work. And again, notice it's to me it's extremely cool because it's the program modifying itself as it's executing. Okay, that's a quick spin through linking.